Hello, my name is Mohamad El-Batal. I'm from Seagate, Office of the CTO, and with me also Hongjian. Fan is an architect and a designer of software who is also going to present the software layer here. I'll start with the Composable Memory Appliance contribution that we just did within the CMS team. And based on that, we actually are in the process of creating the CMA, the Composable Memory subgroup under the CMS working group. And we are inviting people to join the CLA in order to work with us on this. So why memory pooling and memory appliance? The bottom line is, I think, stranded memory is a real problem, and the memory wall situation in terms of compute over scaling beyond what the memory interface capability to keep up from a bandwidth and capacity perspective. And the idea was to expand across multiple nodes, multiple client nodes, to expand the memory capability and provide initially pooled memory, and potentially with software coherency, you can actually do shared memory prior to having hardware sharing as well. So this solution is trying to target about 2 NUMA hops. It's connected via cabling, et cetera, and you'll get more details. But it's the current memory within the server is a single NUMA hop. The current contribution is 2 NUMA hop. In the future, when we go to ASIC technology, currently we are in FPGA mode, and when we go to ASIC technology, we do have line of sight towards faster and lower latency, faster bandwidth and lower latency. The current architecture is basically a 3U appliance that can be a 19-inch or 21-inch solution that currently maps to 2 nodes with full pooling or 4 nodes with partial pooling. We have 8 blades, 8 of these memory controllers that have multi-headed capability. The future solution will be envisioned to be Gen 6, and will support up to 8 nodes with full pooling and 16 nodes with partial pooling. So, currently the current prototype that we actually showed at the Innovation Village is using Samsung 128 gigabyte DIMMs. Each blade has 8 DIMMs. The box has 64 of them, and it basically gives us a terabyte at 400 gigabyte per second with around 400 nanosecond latency. So that's basically what we're able to accomplish at this point in a memory pooled environment. This is the actual booth. I actually added this picture because I knew the booth is closed right now. You can't see it. So, this is the actual appliance that we demonstrated along with the CFM, which is a Composable Fabric Management. The Composable Fabric Manager is a full memory composition tool that provides a GUI or a CLI and actually deals with the various nuances of how do you transfer memory capacity and bandwidth between nodes in a pool. So the work that we actually demonstrated outside, Hongjian is going to go in more detail and show you how we're doing it with which APIs, et cetera. The table, or actually the diagram on the right, shows what we actually can do in terms of latency and how, because we're really not using a switch. We're using a multi-headed memory controller with a crossbar, and it's all based on address decode and is capable of bypassing a switch. No need for the latency adder of a switch. So the configuration, like I was indicating, it can be currently from each server will have to have a retimer We used in the demo Astera retimers, by 16 Astera retimers, Gen 5, and those were put on AIC cards to connect in a mesh architecture. Sorry, I think this thing is not working. Wait. So for, the solution is capable of by 8 connectivity as well. So in an 8-blade system would be by 8 connectivity between each retimer card that is capable of bifurcation. So if the nodes are capable of bifurcation, you can utilize all 8 blades in the appliance. If the node is not capable of bifurcation, it will use half the blades in the appliance and connect, like I said, in partial form. We also, within the server group, we chaired the PCIe extended connectivity group, which spawned PCI SIG effort around the optical working group, which optical PCI now is fully, at least there's line of sight towards productization. We've seen a couple samples from a couple vendors, and we would like to start working on extending short reach optical up to 7 meters for CXL. That's what we believe is needed from a requirement of the OCP specification right now. So with that, I'd like to talk a little bit about the Compositions Fabric Manager. It really is based on standards, APIs, and standard connectivity to orchestration software. And with that, I'd like to transfer it to Hongjian to tell you a little more about it.
Thank you. Hi, my name is Hongjian Fan. I'm under the research group of Seagate. So for this composable memory appliance, we have developed this software. We call it Composable Fabric Manager. The graph shown here is the architecture. On the right is the appliance. Each of the blade has its own BMC, manage the blade itself, and then it's the CXL logic underneath it. On the left side is the management plane, where on the top there is a composer and the fabric management, CFM. We have implemented 2 interfaces. One is a CFM interface, which is based on the hardware logic, and the other one is a Redfish interface. And we also have service client installed onto each server. So those are all Redfish compliant. In the future, we are planning to add what's shown blue here is the memory interface to Kubernetes. We are open to collaboration on that part. Yep. So next page is a closer look or more details on the software design. On the left, we have like different APIs and web UI interface, and in the middle we have the manager layer, and on the right we have the Redfish client, which talks to the memory appliance, talks to the CXL host servers. And this is illustration of the management model. So in order to map a CXL device into a Redfish, we have to decide how do we want to present it. The MTF and the Redfish has some specifications. We abstract our device into a multi-headed and a multi-logical device model, but with a static binding. So this what we based on what's already open in the spec, and we have choose to implement device. In the future, if Redfish has an abstraction for DCD or the dynamic capacity model, we might move to that as well. And this is the CFM model, which we said it's based on the hardware topology. So basically, we have an appliance route, and underneath it, we have the blades route, which has the ports. Each blade should support 2 ports, connects to 2 host servers. And then we have the memory path, which is the composed memory. And on the right side is the host path, where we can show the ports. Each port is a connected CXL device, and we have a memory device to show the physical CXL device, as well as the memory path, which is the abstracted NUMA nodes under system. And here is the Redfish model we have implemented. We have the chassis, we have the fabric, we have the system collections. The collections, the system collections is more to represent the memory appliance, and the chassis we choose it to represent the CXL host servers, and the fabric collections in the middle is it's used for composing and decomposing memory. One thing to note is when we compose a memory, we need to post the endpoint to connect it between the CXL memory appliance to the CXL host. So the CFM CPIs and the Redfish APIs are completely equivalent. So this is the example of API list that's probably most frequently used, and we show both how to use the CFM APIs and the Redfish APIs. Besides those APIs, those are easy for like a machine to use automation and orchestration softwares, and we also provide some tools, nice user interface for human interactions. So here shows the web user interface, which we can see the details of the each blade or each CXL host servers. We see how much memory has been used, allocated, how many devices has been connected, and the compose, decompose memory here. And this one shows the CLI tool. It's another tool for simplification command line use. Okay, call to action. Mohamad, back to you.
Yeah, thank you.
Yeah,
thank you, Hongjian. So, call to action, we created something that basically is contributed, and the CFM is open source. We would like to have you join us within both the CFM subgroup as well as the CMA subproject. And we would like to look at this as a start, as a beginning, as a 0.5 spec, even though when we released the base specification, it's 1.0 because we believe it works. But we want to make sure that the team, the collaborative OCP spirit, is used to improve it and make it something that can be consumed by the OCP customers. So we, again, want to make sure that as a group can actually expand on this. I'll leave some time for questions. All right. If no questions, thank you very much.